in the case of fatigue is usually endurance limit or fatigue strength. Okay. Now there is an endurance limit or fatigue strength value that you get from from tests, basically the RR Moore rotating beam test, and then because we call that SE prime, and then to get the actual SE, that is for the parts that we design, we multiply this with some modifying factors. Okay. To take into account the difference between the test specimen and the actual conditions that you are designing for. Okay. And those differences could be the difference in surface. For example, the test specimen usually have a highly polished surface, whereas the actual part may have different surfaces. Then you have taken into account the differences in size, the differences in type of load, because the test specimen is under only pure bending. You could have torsion or axial load. And remember, this can only take care of pure loading. Okay? If you have a combined loading, and then you would take that into account using the stress parameter. Similarly, you have to take into account the temperature differences and reliability. This once again, remember that this is for 50% reliability. Okay. So, so last thing that we were talking about was KF. So, what is KF? KF is the miscellaneous factor, and this is miscellaneous factor is just a reminder for all the different things that could affect your fatigue life that have not been directly catered for in the other marine factors. So for example, one thing that we talked about last time was corrosion. Okay. So if the environment that you are working on is corrosive, then obviously you'd have to take that into account by lowering your endurance limit accordingly. Similarly, you could have residual stresses. You could have case hardening. You could have surface polishing, and all of these reduce or impact the fatigue life. And maybe directional characteristic such as through cold working, or such as these. Okay. So we start with, for example, talking about the residual stresses. So what are residual stresses? What do you know about it? Anyone? Any idea about residual stresses?
Sir, absence of external load पे जो stresses होती हैं.
Absence of external load पे जो stresses होती हैं, बिल्कुल, very good. So residual stresses by definition are the stresses that are present in the material even when it is not under load. ठीक है? So you can say, so for example, if you are talking about a beam, so it could be a leaf spring or it could be a shaft, for example. So you have manufactured it such that even when there is no load applied on it, so usually we take that if there is no load, there is no stresses. But residual stresses means that you have manufactured something in such a way that even when no load is being applied, there are some stresses already present. There are some stresses already present. So now, in terms of what is we'll talk about how we can have residual stresses. But let at the moment just consider that you have residual stresses. That is, even when the part is not loaded, there are still some stresses in it. Now we know that fatigue is most dangerous in terms of tensile stresses. Because obviously fatigue causes crack growth and ultimately crack becomes critical. So the stresses that are more dangerous for causing fatigue failure are the tensile stresses. So in terms of residual stresses, if the surface and also the fatigue cracks usually propagate from the surface. Both of these things we have already discussed. So in terms of surface, if there are compressive residual stresses already present, then that is beneficial. Because when you would apply a tensile load, the actual tensile load would be reduced. This stress would be subtracted from the actual stress due to load. Okay? So if the surface is already under compressive stress and then you apply load like this, so the tensile stress due to this load would be subtracted from this compressive load to get the actual load. So actual tensile load would be reduced. So the surface compressive residual stresses are obviously beneficial. Whereas the surface tensile residual stresses have an adverse effect. So residual stresses, so in terms of fatigue life or the KF, the miscellaneous factor that you have to take, so that depends upon the type of residual stresses that you have for that part and the loading. So if the loading is such and residual stresses are such that the net effect is subtraction, in terms of tensile stresses, then these are beneficial. But if the residual stresses are tensile, your loading at that point is also tensile, then obviously they would add into each other. So then that has an adverse effect. Okay? So this would be KF more than 1 in the first case, and in this case it would be less than 1. So next quickly, because okay, so let me ask this: how are residual stresses present in a part? Okay. So first we discuss if there are residual stresses, what is their impact? Now, how they are produced in a part? How can a part have a residual stress? Anyone? Have you discussed this before or?
Sir, if the part is produced through cold work.
Okay, ठीक है. नहीं, ये तो आप वो बता रहे हैं कि कोड वर्क जब करते हैं तो रेजिड्यूल स्ट्रेसेस, बट कैसे आ जाती हैं, क्यों आ जाती हैं?
So materials are not completely elastic. So जब loading होती है और unload करते हैं वो
ठीक ठीक, वेरी गुड। शारिज?
जी सर।
हाँ भाई, इसके बारे में कुछ पढ़ा हुआ है, कुछ याद है क्यों होती है?
नहीं सर, अभी दिन में नहीं है।
अच्छा, दूसरा मैंने आपसे क्लास के एंड में जरा क्लास जब खत्म हो तो आप मुझे कॉल कर लिएगा इसी टीम्स पे, ठीक है? वी हैव टू टॉक अबाउट द क्विज।
ओके सर।
Okay, so let me just quickly tell why. So, for example, if you have a leaf spring, and so something like this. So you have manufactured this, and then you bend it like this, okay, so to take it into the final shape. Okay. So you have manufactured it. You would apply some force and you would plastically deform it to take it into its final shape. Okay. So now, as the obviously in bending, obviously we know the highest stresses are at the surface. Okay. So first the surface will yield, and surface would become plastic. Okay. So there would be some plastic deformation in the surface, while the core has remained elastic. So if just magnify this, so if in terms of we are talking about in terms of deformation, okay, so you have elastic deformation and then you have some plastic deformation. Okay. Now, as you remove the load, okay, so material at the core would, because it is elastic, so it would try to return to its original position. But now, because the adjacent material has plastically deformed, so that will not allow it to come into the original position. So would prevent full recovery, you would say. Okay? Because obviously otherwise there would be voids created. Okay? Elastic part would return to its original position while plastic part would not, and that would cause presence of void. So due to that, so the plastic part would stop the elastic part from full recovery, and that would introduce some residual stresses when this load is removed. Okay? So when even that load is removed and the part is in its final shape, you still have some residual stresses. Okay? So now our purpose is that these residual stresses, especially at the surface, have to be compressive. Okay? And obviously, because overall stress, uh, equilibrium, if there are some compressive stresses in the surface, there must be the tensile stresses in core. Okay. So overall, obviously the stress sum would be 0, but obviously because the fatigue crack generally grows from the surface, so that is beneficial. Okay. But obviously we cannot overdo this process, otherwise the tensile stresses in core would be much larger and then they would cause a fatigue crack from the core. Okay. And we don't want that. Okay. And obviously other methods by which we can induce compressive stresses. One is short peening, where we have small balls and that we hammer onto the surface, or you have cold rolling. Okay. Again, that plastically deform the surface. Okay. So all of these processes induce some residual stresses that is compressive in nature, and that is beneficial when the loading is of bending type. Obviously, because there must be loading that causes stresses to be high at the surface to take advantage of the fact that the surface is in compressive residual stress. So any questions from, so generally in swords, gun barrels, so swords is one of historical example that undergoes residual stresses for improved fatigue life. But in modern terms, you have the gun barrels and things like that that undergo springs, leaf springs treatment. So these are also have residual stresses to improve their fatigue life. So another thing that we generally have under miscellaneous factor is the surface plating. Okay. So surface plating generally reduces fatigue life sometimes enormously because it on the surface it induces pores that can basically they are micro cracks, you can say. They are stress raisers, they simultaneously are stress concentrations and also act as surface cracks. Okay. So they generally reduce by a lot, maybe 50% or 60% fatigue life. So in terms of fatigue, they are to be generally avoided. Exception would be corrosive environment, which reduces fatigue life even more. So to prevent corrosion, you could have some plating. Okay. And lastly, I would like to discuss case hardening. Okay. So case hardening once again is procedure where you increase the strength of the surface by, for example, diffusion of carbon at high temperature. So it increases. So if in terms of steel, so if you have so if you increase the surface carbon, so that would increase the SUT at surface. And obviously, so that means that you have a higher SE at the surface, because if SUT is higher than SE, we know is 0.5 of SUT. So that means endurance limit would be higher at the surface. So that is beneficial in terms of that. But again, in this we have to remember that sometimes, for example, so now, if I just amplify this, okay. So you have this, you have case and you have a core, and case has a higher carbon concentration, higher ultimate strength, higher endurance limit. So its endurance limit is higher, whereas the core endurance limit is lower. Okay. So you can say this is SE case and this is SE core. Okay. And now, once again, in terms of bending stresses, we know that, so this is the center line, you can say. So if the stresses are, for example, linearly distributed, so zero at the neutral axis, and stresses are something like that, obviously tensile in nature. So if we compare the maximum stress, it is less than the endurance limit at that point. Okay. But you can see that there is this region, okay, where the stresses are higher than the endurance limit of the core. Okay. So we have to be very careful when the case hardening is present, that we have to consider both SE case as well as SE core. Okay, so any questions from that?
So my question is regarding tensile loading. जब bending load apply करेंगे तो residual load जो हैं जो कंप्रेसिव वाली साइड पे होंगे, एक बेंडिंग का लोड एक तो मैक्सिमम टेंसाइल वाली साइड पे होता है और एक मैक्सिमम बेंडिंग वाली तरफ अप्लाई हो रहा होता है। जो बेंडिंग वाला लोड कंप्रेसिव वाली साइड पे है और हमारे जो रेजिडुअल स्ट्रेसेस हैं वो भी कंप्रेसिव है, तो वहाँ पे कोई एडवर्स इफेक्ट नहीं होगा इसका?
आप कह रहे हैं कि जब बेंडिंग लोड भी कंप्रेसिव है और रेजिडुअल स्ट्रेस भी कंप्रेसिव है, ये क्वेश्चन करना चाह रहे हैं?
क्वेश्चन ये कि बेंडिंग जब अप्लाई करते हैं तो एक सरफेस की एक साइड पे मैक्सिमम टेंशन अप्लाई हो रही होती है और दूसरी साइड पे जो कंप्रेशन वाली साइड, मैक्सिमम कंप्रेशन वाली साइड पे है, वहाँ पे भी अगर रेजिडुअल लोड्स कंप्रेसिव हैं तो वहाँ पे कोई एडवर्स इफेक्ट नहीं होगा?
बिल्कुल। अच्छा, पहली तो अगर हमें जिस तरह की मैंने स्प्रिंग की एग्जांपल दी, तो आप स्प्रिंग को इस तरह डिफॉर्म कर रहे हैं, तो स्प्रिंग जब इस तरह डिफॉर्म करेंगे तो यूजुअली on one side you would get residual compressive stresses and other side you would get residual tensile stresses. ठीक है, so if the loading, इसमें एक बात का ख्याल रखना है कि लोडिंग ऐसी होनी चाहिए, अगर लोडिंग चेंज हो रही है डायरेक्शन में, ठीक है, सो देन आपको कोई फायदा नहीं है, क्योंकि अगर इफ द लोडिंग इज सच, सो फॉर एग्जांपल दिस इज द रिजल्टेंट प्रोडक्ट जिसमें आपने रेजिडुअल स्ट्रेसेस आर सच दैट ऑन द surface you have well, you have some compressive stresses on the surface and obviously tensile stresses, residual tensile stresses at the bottom. ठीक, so अब loading is such that bending is caused like this. ठीक है, and obviously it is changing in magnitude, then obviously it has a positive effect. But if the loading direction also changes, so if the bending moment changes to this, ठीक है, bending moment changes to this, so then obviously it doesn't have any positive effect, because now the residual stresses were tensile on the bottom and now you have a loading that also causes tensile at the bottom. ठीक है, so अगर तो रेजिडुअल स्ट्रेस इस तरह की हैं, तो जिस तरह जो कोल्ड वर्क से नॉर्मली अगर प्रोड्यूस होती हैं, तो उनमें तो यही है कि वो एक तरफ तो टेंसाइल है तो दूसरी तरफ कंप्रेसिव. ठीक है, और actual load should be, you should design the part such that the actual load is reverse of that. So where the residual stresses are compressive, the load is tensile, and where the residual stresses are tensile, the load is compressive. ठीक है, जो दूसरे तरीके फॉर एग्जांपल शॉर्ट पीनिंग है, ठीक है, सो शॉर्ट पीनिंग ओनली इंक्रीजेज द कंप्रेसिव स्ट्रेस ऑन द सरफेस. ठीक है, सो वो ऑब्वियसली शॉर्ट पीनिंग तो आप डिपेंड अपॉन द साइड, सो यू कैन डू द शॉर्ट पीनिंग ऑन दिस साइड and increase the residual compressive stresses on this surface, whereas doesn't affect this side. ठीक, but again, so you have to make sure that the loading is such that only it is in unidirectional type loading. ठीक है, and lastly, if your loading is compressive and the residual stresses are compressive, so obviously in terms of stresses they would be adding up. ठीक है, so the stress would be higher on the compressive side. We would see later when we consider the fatigue failure theories that generally even higher compressive stresses are not very dangerous in terms of fatigue failure. Obviously you have to take care of yielding, so that maybe when they are adding up together they shouldn't cause yielding. Okay? But if they are not causing yielding and they are lower than yield strength, then in terms of fatigue lab they are not very dangerous. Okay? So fatigue cracks generally originate from tensile loading. ठीक है, क्रैक प्रोपगेशन है, इसके लिए you need some kind of tensile loading. It's not it cannot happen under compressive load. It can, but it's the chances are much lower, or you can say probability is much lower, or the speed of crack growth would be much lower. So we don't generally worry about the higher compressive stresses. It's the tensile stresses that are that we are mostly concerned with. बिलाल ये पूछ रहे थे यही बात है. Okay. Anyone else? Okay. So next, before moving on to the problems, we would consider the last topic in this fully reversed loading, you would say, that is the fatigue stress concentration factor. Okay. So fatigue stress concentration factor, and obviously there is a associated topic of notch sensitivity. So we have discussed about stress concentration factors when we studied static loading, and we said that for static loading we generally take for ductile material, for only the case of static loading we take this stress concentration factor into 1. Okay? We don't consider this stress concentration factor for static loading. So this is a particular case in ductile materials. Why we take that equal to 1? Because under static loading there is some local yielding generally at the point of highest stresses, and that local yielding causes stress relief, the stress is to be lower, and ultimately when the whole not until the whole material is yielded that the failure happens. Okay. But we cannot ignore this stress concentration factor under fatigue loading. Okay. We know from the mechanism of fatigue that fatigue basically fails this mechanism of local yielding that stops crack growth in static loading, but in fatigue loading, because of the load reversal, the crack still continues to grow. So anywhere that you have notches, grooves, keyways, section changes, okay? And these are part and parcel of any mechanical part. You cannot avoid that. Okay? You fillets, holes for joining. Okay? So all of these okay? So all of these cause stress concentration. Okay? So we already know from our study of static loading that the stress concentration factors, you have KT, how they are determined. So these are called the geometric stress concentration factor, generally used as it is for brittle materials. Okay. Now KT measured experimentally or using FEM is used as it is for brittle material. For ductile materials, we take KT is equal to 1 under static loading, and under fatigue loading. So fatigue loading, we have to consider the stress concentration factor, but it is not the same as KT. For ductile material, under fatigue loading, so you still have the effect of stress concentration, but the effect is still not as large as it is in brittle material. So the stress concentration, the fatigue stress concentration for ductile materials under fatigue loading is between 1 for static loading and KT. Okay. So it is somewhere between this geometric stress concentration factor that is irrespective of material and only considers geometry, and one that is obviously for ductile material under static loading. Okay. So why still there is some reduction from KT? This reduction is obviously due to the local yielding. Okay. So local yielding still has some effect of reducing the effect of stress concentration, but the effect is not as large as it is in static loading. Okay. And that local yielding, we generally characterize it by a term that we call notch sensitivity. So as is the topic, that is stress concentration, fatigue stress concentration factor and notch sensitivity. So what is notch sensitivity is a parameter that depends upon material. So it depends upon material and notch radius. Okay. So as the name suggests, this notch sensitivity, that is characterizes the local yielding and depends upon the material and notch radius, says that obviously if this number is higher, okay, so let's talk about this number. So notch sensitivity generally denoted by Q, and Q has values that range from 0 to 1. So if Q is 0, so that means that your particular material and notch radius is not sensitive to crack. Not sensitive to crack, or you can say notch. While Q is equal to 1 means highly sensitive. Okay. So obviously we want to reduce the notch sensitivity. Okay. And if we are talking about in terms of fatigue factor, so that Kf is we say is related to Q and Kt by this factor, that is Q, notch sensitivity. Okay. So let me just quickly recap. We said that Kt is a stress concentration number that is for keyways, holes, etc. that is determined by geometry, and we use it as it is in brittle material, but in ductile material is its effect even under fatigue loading reduces due to local yielding. That reduction is taken care by this factor that is known as notch sensitivity, denoted by Q. So if Q is 0, then that means that Kf is equal to 1. Okay. So that is the condition where basically we are talking about no effect of stress concentration. Okay. So that means that your particular notch is not sensitive. Okay. Whereas when Q is equal to 1, so that means that Kf, in this case, if Q is equal to 1, then Kf would be equal to Kt. Okay. So that means that you would be taking the full effect of the geometric stress concentration factor. The notch is highly sensitive. Okay. So generally it is somewhere between Q0 and Q1, more closer to 1 than 0. Okay. And again we have the experimental data that we use to measure this. So this we have already talked about that any notch, etc., causes stress concentration in the material. Stress becomes higher in the vicinity of the region of discontinuity, and usually we have stress concentration factors, KT, geometric stress concentration factors, that tells us, that we have found experimentally, that tells us how much the stress has increased in this region. Now, ductile material under static loading do not have any effect of this stress concentration, but under fatigue loading, they cause the effect. It is somewhat reduced due to local yielding, and that effect is taken care by a term that we call notch sensitivity. Okay. And this is, you would say, experimental results. So these are the strength, and this is the notch radius. So if we analyze this figure, so it basically is saying two things. Okay. So the more ductile the material, the less notch sensitive it is. Okay. So you can, if I summarize what is given in this figure, so you can see that more ductile the material. So in terms of steel, obviously we are talking about reducing the carbon content. So if you reduce the carbon content, that reduces the strength, increases the ductility. So the strength is reducing. So that means the ductility in terms of steels, that means the ductility is increasing. So this 400 megapascal SUT steel would have higher ductility than this steel, and it would be less notch sensitive. Okay, so you can see that this notch sensitivity number is decreasing. So more ductile material, you have larger local yielding, so lower notch sensitivity. Whereas in terms of notch radius, so this maybe a little you can say non-intuitive. So notch, when the notch radius reduces, okay, so the sharper the notch, so in terms of edge, so if you are you have a section chain, and this R, the smaller this R, okay, so that means this notch radius. So when this decreases, your notch sensitivity is reduced. Okay, so that means for so there are two ways to reduce notch sensitivity. One is to use more ductile material. Second is for lower R. Okay. So you have once again both more ductile material or lower R cause higher local yielding. Okay. So if you increase the local yielding, you would lower the notch sensitivity. Now, this second part maybe on the face of it maybe sound a little contradictory, because whenever we have talked about stress concentration, we have talked that to reduce stress concentration, we should increase this radius. Okay. We should have large fillets. Okay. So that is what we have studied before. Okay. And that is obviously still true. Why is that? Because by lowering R, you are reducing notch sensitivity. That is okay. Okay. But you are also so by lowering this R value, so reducing the radius at the notch, okay, you are reducing Q value is going down, but at the same time KT is going up, because we also know that KT also depends upon the notch radius. Okay, so for example, in this figure you can see that so this is for a hole, but again in the hole you can also see that as the W ratio reduces, so the notch sensitivity increases. Okay. The KT increases. Okay. So by lowering R, you are reducing Q, but you are increasing KT. Okay. So geometric effect of stress concentration. Okay. And generally, this effect is much larger than the effect of Q. Okay. So you would not be better off by lowering R, because ultimately the KF would still increase because of this KT increase, even though Q is reduced somewhat. Okay. So that lesson that we have already known, that if you have section changes, holes, key base, you should have as generous a fillet as possible. Okay. And this Q value in ductile materials, as we have seen from the figure, generally varies between this range. Now we have studied this with the Marian factor, but this Kf, remember that Kf we can still use this with strength parameter Se by dividing that with this factor and lowering the strength, but generally we use it by multiplying it with stresses, okay, to get the maximum stress. Because if we use it with the strength, then there's a problem occurs when the when we go for combined loading, and you have for example torsion involved, and for torsion you have a different stress concentration factor. Different types of loading, you have different stress concentration factor, so you don't have one factor that you can divide the strength value with. Okay. So it is better to take care of it in terms of stresses. Okay, and we will do that in this course. So, any questions? Okay. So let me now move first problem from these topics. So now just to recap before going into this problem, that we have for the stress life method, we have learned everything that we have to have to do with the strength parameter. Okay. And all of the what we have discussed basically deals with pure loading. Okay. So if you have pure bending or pure torsion or pure axial load, then we know how to design a part under fatigue loading. Okay. So the only thing left is when there is some combination of these. One, that there is a combination of axial bending and torsion, and another thing is the effect of mean stress. Okay. All of the discussion that we had about the stress life method, the endurance limit, the modifying factor, is applicable directly to the cases where the load is fully irreversible. Okay. So you have, so for example, a load of 10 kilonewton. So that means that load is such that it is plus minus 10 kilonewton. Okay. So for this case, or moment is plus minus 10 Newton meter. Okay. So for these case, we have learned everything that we have to know, and we can design for these cases. But when you would have a case from M, for example, 0 to 10 Newton meter, okay, so then you obviously, the mean stress is not 0. In these cases, the mean stress, if you draw the stress cycle, so it is such that the mean stress, because it is varying from 10 to minus 10, so the mean stress is 0, and same for this case. But in this case, there is some mean stress. Okay? So these two things we ought to know, and we would discuss in the upcoming lectures. Okay? So what to do with mean stresses, and what to do when the axial and torsional and bending stresses are there simultaneously. So in this problem, we have a rectangular bar that is cut from ASI 1018 steel flat. The bar is 60 millimeter wide. So if I draw the figure as well, so you have a bar that is 60 millimeter wide, and you have thickness is 10 millimeter, and we have a hole of 12 millimeter. So you have a hole with a dia of 12 millimeter, and that we have seen already the same figure, that the stress concentration factor we have seen in the stress concentration factor top. Now the bar is loaded in a push-pull fatigue by axial forces. Okay, so you have axial forces denoted by FA, and they are obviously changing from some positive value to negative value. And they are uniformly distributed, so the stresses produced by them is uniformly distributed, and this is the design factor that we have to use. So we have to estimate the largest force that can be applied ignoring column action. So obviously when this force becomes compressive, there is another kind of failure that is due to buckling can occur. So that has been, so we are asked to ignore that. So so where to start? Obviously, so once again, remember this is a problem that we can do because the loading is first pure. There is no bending or torsion involved with axial, and the load is completely reversed. Okay. So that is why all of our discussion in terms of strength is directly applicable. Okay. So we start with the material. So we have SI 1018 steel given. So we look in the appendix 820 for, in this case, to get the ultimate strength for this material, that is 440 megapascal. To estimate the endurance limit of the test specimen. So for test specimen, that is SE prime, we know that it is related to the ultimate strength by this formula for ultimate stresses, strengths less than 1400 megapascal. Okay, so that would give you basically 220 megapascal. So that is the endurance limit for the test specimen. So now next we have to find what will be the endurance limit for the actual specimen. Okay. So actual specimen endurance limit would be reduced from this by using this marine equation. So starting with Ka, that is the surface factor. So that takes into account the difference between the polished specimen of the rotating beam test and the actual specimen. So our actual specimen is cold drawn. Okay. So in the surface finish, we said that we have different surface finishes, different equations for different surface finishes. You had the ground finish, you had cold worked on machine, you had forged, hot rolled. Okay. So for this, and for all of that, we have formula something like A, S, U, T, and B, and this value of A, B changes for different surface finish. So for cold work finish, this is applicable. So that gives us the surface factor of 0.89. The KB is the load factor, and we learned that we take the load factor equal to 1 for axial loading. If the load is bending, then obviously there is some load factor, but if you for axial loading, this is equal to 1, and this size factor. So size factor is 1 for axial loading, whereas the load factor Kc is 1 for bending load, pure bending, and 0.85 for axial loading. And for reliability, we have in the problem statement, there is nothing about reliability or temperature situation or some miscellaneous situation. So we have to take all these factors equal to 1. Okay. But remember that this design is for, that would mean that this design or the load that we would determine is for 50% reliability. So if you need to increase the reliability, you need to increase this factor. So, so that gives us the actual strength of the part would be so 0.89 into 0.5 into so that would give us the nearest limit of 166.43 megapascal. Okay. Now, to obviously find the load, we have to compare this strength using the appropriate safety factor with the stress. And stress in this case, the stress, obviously the simplest of cases, stress is F over A, but due to this pole, obviously the higher stresses would occur on this plane. So in terms of area, you have to take care of that. And for this geometry, we have to have some Kf. Okay. So now this Kf depends upon notch sensitivity as well as the geometric stress concentration factor. Okay. So first, if we, for example, so go to table 15.1, so that is the scenario that we have to discuss. Okay. So, so this is the loading that is given to us in our problem. So for this, so R values for D and W, that is 12, and width is 60. So that would give you dW ratio of 0.2. So that would mean that would mean so 0.2, this KT value is somewhere around 2.5. And for Q, obviously we have to look at the notch sensitivity table. Once again, we don't have to be very accurate with this. Okay. So in our case, strength is somewhere around 440 megapascal, and the notch radius is 6 millimeter. So 6 millimeters obviously of the this graph. So we just had to estimate. So if you are looking at 440 megapascal, so that would be maybe a little higher than this figure. Okay, so somewhere like this, and we have to extend it in this direction. So we can estimate that the Q would be somewhere near this value. Okay, so Q would be somewhere near 0.8. So that is good enough for us. So that would mean that this is, so our this factor reduces by to 2.2. So this is still a significant effect, but it reduces somewhat. So the stress produced by this load, A is for alternating. So A would be 2.2 into FA that we have to find, divided by this load area. Obviously, the area we would take the minimum area, and that is in the vicinity of the hole. So you would subtract 12 from 60 and you multiply it with 10. Okay. So now we have the stress and we have the strength, and we can compare it with the safety factor. So this should give you the safety factor, that is 1.8. SE is 166.43, whereas this F. So if you solve this, you get FA divided by something like this. So just rewriting this equation in terms of so this gives you something like 20.35 kilo Newton. So that is the maximum alternating load that we can apply without causing fatigue failure. Okay. For this kind of geometry in ASI 1018 steel. And we are designing for infinite life in this case. Okay. So we have used SE. Okay. So we have designed for infinite life. So any questions from this?
इसमें KD के और KF वन क्यों लिया इसमें?
KT और KF में क्या कह रहे हैं?
सर वन क्यों लिया हमने?
KF1 नहीं लिया हमने, KF1 नहीं लिया हमने, KF की वैल्यू 2.2 ली है इस केस में।
सर वो जो हमने KC 0.85 फाइंड किया ना, KD KE और KF हमने इक्वल टू 1 किया।
बिल्कुल बिल्कुल, KD KE KF हमने इक्वल टू 1 किया। वो इसलिए किया है बिकॉज KD जो है वो रिलायबिलिटी फैक्टर, ठीक है। टेस्ट स्पेसिमेन की जो रिलायबिलिटी है, दैट इज जो टेस्ट स्पेसिमेन की वैल्यूज हैं दैट आर फॉर 50% रिलायबिलिटी. So if you need more than that, you would increase that. But in our problem statement, there is nothing about increase in reliability. हमें मशीन सरफेस मशीनिंग का बताया, ठीक है। हमें obviously एक्सियल लोड का पता है, तो हम KB और KC के हिसाब से ले सकते हैं. But there is nothing about increased reliability. So even if we want to take this factor, we won't be we don't know what value to take because we don't have a target reliability. So if you have a target reliability of 90%, you can take the appropriate reliability factor. Again, KE is for temperature. So again, the temperature effect it is inverse. KD is for temperature and KE is for reliability. So temperature, once again, we are not in the problem statement given that this we are maybe working at higher temperatures. So we are not given something like that. So we cannot take. You see, similarly KF, so we have nothing about residual stresses, corrosion or something like that. Okay? So we cannot take these factors anything other than 1 because there is no information about those given in this problem statement. Anyone else?
सर वो नॉच वाला दोबारा समझा दें, KF और KT।
क्या उसमें क्या कंफ्यूजन क्या आ रही है?
सर जो हमने नॉच कैलकुलेट किया, D/W वैल्यू कैलकुलेट किया और उससे जो इवेंचुअली KT और KF कैलकुलेट किया।
अच्छा, कैलकुलेट की बात करें ऑब्वियसली। अच्छा, पहले तो ये चीज क्लियर होनी चाहिए अगेन, KT इज द ज्योमेट्रिक स्ट्रेस कंसंट्रेशन फैक्टर यूज्ड एट एज इट इज फॉर ब्रिटल मटेरियल्स, and KT is equal to 1 we take for ductile material under static loading. For fatigue loading, this value is KF, denoted by KF, and it is somewhere between KT and 1. Okay? And it reduces due to notch sensitivity. So higher notch sensitive the material is, the more it is closer to KT. Less notch sensitive it is more closer to 1. Now the value कैसे find करेंगे? First you have to find the value of KT. So KT की value कैसे find करेंगे? You go to this table that is A15 and there are multiple figures related to your particular geometric discontinuity and loading. ठीक है? So even for this plate with a hole, had the loading been pure bending, you would have to go to a different figure. So this figure is appropriate for our case, where you have axial loading and flat plate with a hole. And so this D/W, so you are given in figure what is D and W. D is the size of hole. So in our case it is 12, width is 60, so that gives us ratio of 0.2. Okay. So you go on this figure on this line, so 0.2, and this value is the value of KT, so it is equal to 2.5. So to find the fatigue stress concentration factor, the other thing you need to know is the value of Q. So for Q value, Your book also has equation for finding a Q value, but that equation is applicable only for SUT in terms of US customary units. Okay. So if you want to use, you can do that by converting first the stresses from strengths from megapascal into kpsi and use that equation. So that equation is obviously valid even for this range. But the figure, if you look at the figure, and I won't suggest you to use that equation. I would suggest you to use this. So the figure is up to 4 millimeter. Okay. So our case is obviously of 6 millimeters. So that would be, so if you take the same scale, so that would be somewhere around here. And obviously you know that you are reading the values from the figure, so you don't have to be very accurate with this. Okay? You just need to know that you know what is, where to look for noise sensitivity, and in this figure where to look. Okay? So if by your value this impression is created that you know this, so that is okay. Okay? So you don't have to be 100% accurate with this. We know that even this data has so much scatter that there's no point in being trying to be very accurate. Okay? So this you can see that these lines are denoted in terms of gigapascal. So so that means that this 0.4 is basically 400 megapascal. Now our material, we were given 1018 steel, so that means this line is 700 megapascal, this is 400 megapascal, so 440 megapascal would be closer to this line but on the upper side. Okay? And then if you extend this, okay, somewhere like this, so you can see that it would be closer to this line. Okay? So Q value of 0.78 or 0.8 or 0.82, these are all, I would say, okay for this case. Okay? So if you take Q is equal to 0.9 or 0.95, then that would not be good. But if you take Q is equal to 0.8, or if you, for this case, if you had said that Q is equal to 0.6, so that doesn't make any sense. But Q is equal to 0.8 or 0.75, or that is all okay, I think. Okay. Anything larger than this value taken would be okay. So using these two values, obviously we get the value of kf that would be lower than kt somewhat, but probably close to it. So it gives us 2.2. Any other question? Okay, so we move to another problem. So remember that in this design, because we were not given anything, we designed for infinite life. Okay, so we weren't. This is the same problem. Let me just copy a different problem. Okay. So now this is more of a design problem that we have a scale rod that is cantilevered at one end. So that means that the load is, we are talking about bending, and the rod is length is given 0.6 meters, so 600 millimeter, and supports are completely reversing. Again, everything we are discussing is only valid for completely reversed load, okay, of plus minus 2 kilonewton. Now the material is 1080, so hot rolled steel. So 1080 means, it's again these things you should know. I'm repeating it again and again. 1080 means higher carbon content. 80, all the problems we are discussing usually would have 1020, 1040, 1060, 80. So this last two digits stand for carbon content. So this has 0.2% carbon, 0.4, this has 0.8% carbon. Higher the carbon content, higher is the strength, lower is the ductility. So ASI 1080 steel would have much higher strength value than ASI 1018 that we used in the last problem. It is hot rolled. Okay. So if the rod has to support this load for 10 raised to power 4 cycles, so we are talking about now not for infinite life, we are talking about 10,000 cycles, and the design factor is 1.5 that we have to use. So what would be the dimension of the square cross section? So we are talking about only a square cross, right? Not a rectangular, because that would again introduce an extra variable. So where to start from? So now we know the procedure, we have solved one problem, so कहाँ से start करें? So now I think you can participate more and tell me what to we can have a discussion about that. कहाँ से start करें?
सर टेबल A20 से इसकी अल्टीमेट टेंसाइल स्ट्रेंथ निकालेंगे सबसे पहले।
बिल्कुल, वेरी गुड। अल्टीमेट टेंसाइल स्ट्रेंथ हमने टेबल A20 से देख ली, दैट वुड बी 770 मेगा पास्कल। ठीक है, सो लास्ट क्वेश्चन में 440 थी, यहाँ 770 है, दिस इज मच हायर, सो एज यू शुड नो 1080 की हायर। ओके, सो नेक्स्ट obviously we have to go towards the endurance. We need this the fatigue strength at 10 raised to power 4 cycles. So how to go to that? कैसे find करें? फटीग स्ट्रेंथ हमने फाइंड करनी है, कैसे फाइंड करेंगे? अल्टीमेट स्ट्रेंथ हमें पता लग गई मटेरियल की, ठीक है, तो ऑब्वियसली फ्रॉम अल्टीमेट स्ट्रेंथ वी कैन इजीली फाइंड द एंड्योरेंस लिमिट फॉर द टेस्ट।
एंड्योरेंस लिमिट फाइंड कर लेंगे।
हाँ, एंड्योरेंस लिमिट फाइंड कर लेंगे पहले टेस्ट स्पेसिमेन की, that is 0.5 SUT, so that would give you 385 megapascal. And then you have to find, because we have to find not the fatigue strength at this cycle for test specimen, but for actual specimen. Okay? So we won't use SE prime, we would use SE. And SE, again, you have these factors that have to be multiplied with SE prime. So starting with the first factor, that is the surface factor. सो सरफेस फैक्टर में कौन से हमने ए और बी के लिए कौन सी हमने इक्वेशन देखनी है, कैसे पता लगेगा इस प्रॉब्लम में हमें क्या चीज दी हुई है, सरफेस कैसी है, व्हाट इज द सरफेस फिनिश?
हॉट रोल्ड सर।
हॉट रोल्ड, बिल्कुल, वेरी गुड। सो फॉर हॉट रोल्ड यू हैव 57.7 into SUT is 770 and 0.718, so that would give you surface 0.488. Okay. So once again you can appreciate this thing, these are in terms of numerical, बट सिर्फ ये नहीं आना चाहिए कि यार ये के की वैल्यू कैसे निकालते हैं, ये पता होना चाहिए कि यार हॉट रोल्ड का क्या इफेक्ट है। सो यू कैन सी दैट हॉट रोल्ड हैज अ वेरी सिग्निफिकेंट इफेक्ट ऑन द फटीग स्ट्रेंथ। ठीक है, देयर इज अ सिग्निफिकेंट रिडक्शन एंड वी हैव टॉक्ड अबाउट व्हाई दैट इज द केस, because obviously hot rolled, one is the surface finish is not very good, and secondly because you are heating it, so that causes decarburization at the surface, so that also reduces the surface strength, so that is why this effect is very large. Now Kc, that is the load factor, we know is 1. So what about Kb? That is the size factor. साइज फैक्टर क्या लें? What is the size factor? First size factor you should know is for, because our case जो टेस्ट स्पेसिमेन की वैल्यू है ये जो SE prime है, that is for completely reverse bending. ठीक है. Now our case one is you have the specimen size is the case is different because the cross section is not circular, it is square, it is non-rotating. ठीक है. So all of these effects are to taken care with the size factor. ठीक है. And obviously for calculating the size factor we need to know the dimensions. ठीक है. And generally this is a typical of machine design problem that this is not completely problem that from where you have A, B, C, D given and you have to find E, you have to go through this procedure, but we have to do some iterations. Okay? So as a typical machine design problem, you have to do that. So we would at this time we would assume some value of size factor, and then at the end when you have the dimensions, you can again come back to this size factor and calculate the real size factor that you have for this problem. Okay. So at the moment we assume some value, so 0.85 is a typical value. This is the range 0.8 to 0.9 that the size factor usually is in. So we just assume 0.85 and we will see what is the actual size factor when you have the dimensions for this problem. Okay. So KB is equal to 0.85, so that gives you the SE value, so 0.488 multiplied by 0.85. Rest of the factor, because there is nothing about temperature, once again reliability, so miscellaneous, so we take them as 1, and so we multiply it with 385, so that gives us the SE equal to 160 megapascal. Okay. So in the last problem we had 1018 steel and the SE was 166 megapascal. Here we have a 1080 steel that has on the face of it much higher strength, but ultimately the endurance limit for the part is lower than that was for 1018 steel. ठीक है. So ये चीजें साथ साथ नोट करते जाएं. Now we need to find SF, and for that we know this relationship. SF is again on a log-log graph. We know that it's a linear relationship between the number of cycles and the fatigue strength, culminating at 10⁻⁶ cycles where you get the endurance limit, and 10⁻³ cycles where you get some fraction of ultimate strength. Okay. And these A and B are material related parameters related to found by these equations. Okay. So first you have to find this F value, and this F value for this we would have to go to this graph, and this graph is given in megapascal in your SI edition book. ठीक है. So जो आपके पास हार्ड कॉपी है जो उसमें ये SI edition में है, so you can directly read from this. ठीक है. So for our SUT that is 775 megapascal, you would have to read what is the value of F. So that turns out to be somewhere around 0.83. Okay. So that means in this case this A would be equal to 0.83 into 770 square divided by SE, that is 160. So previously we used this equation with SE prime, but then we were finding the fatigue strength of a test specimen. Okay, but now this is the fatigue strength of the actual specimen, so we would use SE. So that would give the value of A as 2553 megapascal. Remember, this A has unit of megapascal, the B is unitless. So -1/3 log of 0.83 into 770 divided by 160. So that would give you minus 0.2005. So this SF would be equal to 2553 into now you can have any number of cycles. So our required number of cycles are 10,000. So you put 10 raised to power 4 here. So that would give you the fatigue strength equal to 403 megapascal. So now you have much larger strength value to play with. The endurance limit was 160, but that is for a million cycles. We have reduced the number of cycles to the large amount, that is we are only looking for 10 raised to 4, 10,000 cycles. So here you have much higher strength value, that is 403 megapascal. Okay. Now in this case, so we have the strength value and we have the the design factor, and also there is this. So we have to neglect any stress concentration at support. Generally we don't do that, but in the problem statement it is given to neglect the stress concentration. So we don't apply, we would not multiply the stress with Kf. So stress in this case, so maximum moment occurs where the maximum moment occurs, there would be the maximum stress. So maximum moment would be at this end and would be equal to this 2000 multiplied by 600. So you have 1200, you can say kilonewton millimeter. Okay. So the maximum stress would be equal to this maximum moment multiplied by the distance from the center to the outer point. So that would be B by 2, and to the divided by I. So the moment of inertia in this case is 1/12 bh cube. So B is the same, so B into B cube. So this is for maximum stress. So we have to equate it with our strength, fatigue strength value using suitable safety factor. So you get SF divided by the safety factor, that is 1.5, and equating it to this maximum stress, that solving this we can 72 into 10 to the power 3 divided by B cube. And this is in megapascal, the unit Newton millimeter I am using. So you replace this with 403, solve for B. So this gives you about 29.9. So we round out to that to 30 millimeter. So that is cross-sectional size 30 by 30. That would be probably safe for this case. The one thing left is the size, the actual size factor. So we assumed KB is equal to 0.85. So now you can find out the real KB, and first you have to go into look at the table to get equivalent diameter. So size factor, obviously, if there's only bending, then you have the direct equation that relate diameter to size factor. But if you don't have a non-rotating case or non-round case where the cross section is not round, then you have to go for equivalent diameter, and in this case the relevant equation is this. So that gives you the equivalent diameter as 24 millimeter, and for 24 millimeter the size factor was equation is so size factor turns out to be 0.88. So for our size 30 millimeter, you have a size factor of 0.88. We took, in solving this, we took KB is equal to 0.85. So you can go for another iteration by solving it for 0.88, and then obviously this size factor, this B value would be somewhat lower than that. But 30 millimeter is also okay because we are on the conservative side. Okay? Because KB is, we took KB is equal to 0.85. Now, had the KB been somewhere maybe lower than 0.85, अगर ये 0.88 की जगह 0.83, 0.82 वगैरह को वैल्यू आ जाती तो फिर लाजमी हमें दोबारा इटरेशन करनी पड़ती. But in this case, because we are on the conservative side, B is equal to 30 millimeter is still okay. But if you want more accuracy, more efficiency, so you can want to reduce this cross-sectional size, so you can go for 0.88, and then it would reduce somewhat, and for that again more accurate KB, and it would maybe converge in 2-3 cycles of iteration. So any questions from this?
सर वो क्विज का बता दें, अभी थोड़ा टाइम रह गया तो.
क्विज का बता दें. अच्छा, क्विज का बता दें. ठीक है. तो पहले अगर कोई क्वेश्चन है तो क्वेश्चन जरूर आंसर कर लेते, फिर क्विज का बता देते. कोई क्वेश्चन नहीं है? नो क्वेश्चन.
सर एक्सक्यूज मी सर.
जी 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 जी
सर जो हमने डिजाइन फैक्टर लिया है केबी,
जी जी
साइज फैक्टर सर.
केबी
सर केबी सर केबी साइज फैक्टर.
अच्छा, साइज फैक्टर.
सर आप हमने 0.85 लेके इसको सॉल्व किया पूरी क्वेश्चन को आगे लेके
जी
चले
जी
इससे.
जी
सब
जी.
जब के बी की वैल्यू दोबारा निकालेंगे तो सेम नहीं आनी चाहिए, क्योंकि बाकी वैल्यूज तो उसी से आई है ना सर.
नहीं, बाकी वैल्यू उससे आई है मतलब क्या, क्या मतलब है इसका? बाकी
सर
वैल्यूज कौन सी?
सर केबी हमने केबी 0.85 लेके सॉल्व किया ना क्वेश्चन.
बिल्कुल.
तो सर जब हम उसकी दोबारा वैल्यू निकालेंगे इसी क्वेश्चन से तो वो सेम नहीं आएगी.
बिल्कुल सेम नहीं आएगी, क्योंकि 0.85 तो हमने अज्यूम किया ना केबी की वैल्यू है. ठीक है, और हमने उससे कहा कि अच्छा ये क्रॉस सेक्शन है. बट केबी तो साइज फैक्टर है, साइज वो तो साइज पे डिपेंड करता है ना. हमें केबी की एक्चुअल वैल्यू तो हमें पता ही नहीं थी, क्योंकि हमारे पास केबी का साइज ही नहीं था. ठीक है.
ओके सर.
अब जब हमने साइज, एक्चुअल साइज कुछ वैल्यू हमारे पास आ गई, कोई राउंड अबाउट वैल्यू आई, अच्छा चलें जी 30 मिलीमीटर है, तो अब 30 मिलीमीटर के लिए हम देखेंगे कि 30 मिलीमीटर के लिए साइज फैक्टर होना क्या चाहिए. तो 30 मिलीमीटर के लिए साइज फैक्टर आ गया 0.88. बट ये भी एक्चुअल नहीं है, क्योंकि अब आपने 0.85 यूज किया, उसके लिए 30 है और साइज फैक्टर 0.88. अब 0.88 अगर मैं यूज करूंगा साइज फैक्टर, तो फिर साइज और कम आ जाएगा, मतलब
सर यही बात मैं कर रहा हूं.
28 आ जाएगा. अब 28 के लिए साइज फैक्टर 0.88 नहीं रहेगा. ठीक है ना. फिर
वो कम
आप
हो
दोबारा
जाएगा.
साइज फैक्टर कैलकुलेट करेंगे, फिर दोबारा इटरेशन करेंगे. तो इसी तरह की 2 3 4 दफा जब आप इटरेशन करेंगे तो ये वैल्यूज कन्वर्ज हो जाएंगी, क्योंकि बेसिकली आप क्या करेंगे, यू आर सॉल्विंग इट न्यूमेरिकली. ठीक है, क्योंकि the variables are more than the number of equations we have. And that is generally the case with design. डिजाइन में आपको डायरेक्ट 100% एनालिटिकल सॉल्यूशन को एक डिजाइन तो नहीं है, you have multiple solutions.
ओके सर.
उमर, okay, any other question?